if you have homework, just turn it in maybe after we finish up. So just put in this stat right before you leave. If you've had a printer mishap or something like that, please slide it under my door. My office is on the syllabus, if you don't know where I'm at, but I'm in 401A. That's just in this building. Any questions about the homework? Illuminating? So that asymptotic thing is weird, isn't it? So the asymptotic walled interval, those asymptotic approximations sometimes are good and sometimes are horrible, and it depends on the conditioning of the data. So Bayesian methods tend to work because you condition on the data and you're not asking for, just necessarily what's called an a priori coverage set or coverage interval. I'm going to show you a couple examples also to compare and contrast Bayesian intervals versus frequentist coverage type intervals. I'll give you something that's exact coverage, but the interpretation is a little bit mangled. And then I'll show you what a Bayesian does, and conditioning on the data gets something right. Also, the prior can help you out. So it can act as a regularizer in weird bounding spaces. It seems to do approximately the right thing, at least in the ballpark. What did you think N was? To guarantee using the walled interval you were within 1% of the 95% interval. So I wouldn't, if you reported something and you said it's 95% coverage, but in reality it was 94%, I'd say, all right, we're talking about the same thing. But if it was really like 70%, give me a break. You're reporting something and you're saying a mathematical statement that does not hold for the inference that you're actually doing. And people not checking what their actual coverage rates are in the situation that they're in, I think is poor form. So, but you see it a lot. What did you think N was to be within 1% of the nominal rate? So the nominal rate's 95%. If you were within 96 to 94% coverage, I would say that's within my standard, maybe. It would depend on the context of the problem and what 1% meant to me. Obviously, if you're forecasting something really important, maybe that's not close enough. What do you think N was? 2,600? Maybe something like that? Sam?
For the frequentist?
Yeah.
I think it was like 2,000 to 3,000, I thought.
Maybe, right?
I haven't worked that in days, but...
Anybody else?
I got something more.
So what did you say?
I didn't think that you could completely guarantee it until something like over 10,000.
Yeah, I think it's like that. So you could be within 95 or within 1% at around the 2,000 mark. But what's weird is that you might hit these little moments where all of a sudden it falls apart. And this is a little bit counterintuitive, and I think people sometimes think they have errors in their code. Sam sent me a really good illustration, and it looked like this. So I think P was, about 0.01. Is that what you used? I'm not going to draw the axis to scale. This phenomena happens for all P. It's worse near the boundaries. If we made this even smaller, it would be even more troubling. So as a function of N, you could plot this coverage rate. So coverage, 95%, let's say it's here, so I've standardized everything to 95%, so I'm just looking at the frequency and not the actual counts. We'd like to be somewhere around here. So this would be within 1%, so that would be like 96%, and that would be 94%. If you were in here, I think it's pretty good. And it does, kind of like in a simulation study, you'll always have this little bit of jigging and jagging, and if you repeat the study more, this will smooth out. And it'll come up, and you might think, hey, that's pretty good. So you may have just increased N until you got there, and then all of a sudden, you're like, oh, if I keep increasing N, it should only get better. I think a lot of people have that intuition, but because of the discrete nature of the problem, certain combinations of N and P, weird things can happen. So just like that jigging and jagging as you plot it over P, things fall apart near the intervals. There's some jigging and jagging you kind of do about 95%. and then it goes over 95% and it ducks under 95%. And that's because of the discrete nature of things. You're asking for 95% and it's not always possible. But this can be drastically worse than you really think. So what this will do is it will increase and then it will drop. And it will drop abruptly at one value of n. And then it'll come back. And it'll go up. And then it'll be good for a minute, and then it'll come down. Again, this distance will be a little bit less than that one. And it'll go up. So, and then boom. It'll keep doing that. And so, what Christian is saying is he's even concerned about those little gaps right there. So he marched through this until that gap right there was only 1% away from the nominal rate. That is highly perplexing. And I don't think a lot of people understand it. Saying that, there's papers written on this. So if you look at coverage for the walled interval, you'll see a slew of papers that people have written. People are aware of this, but sometimes you still see this stuff. When I see asymptotic frequentist talks, I'm always curious about this phenomena. I'll always ask them about a simulation study. So if you're a frequentist, you can repeat things over and over and over again. That fits into the paradigm. Doing simulation studies is inherently frequentist. I think they're a good idea even for Bayesians. See the, performance of everything. Anyway, I don't like that walled interval. I don't like that we teach it. So I don't like that we always paint this rosy picture. In undergrad stuff, it's like, well, here's the correct answer for the test. But in practice, this is much worse. But you should do it anyway. I don't like that messaging. So I can appreciate why once upon a time somebody came up with this. And it was useful and it was easy to do, but I don't think people understood all this jumping right here. Let me just ask you a question. As a function of n, is this converging to 95%? Yes, it's convergent. What type of convergence is this? I want to test you on types of convergence, but obviously this is a weird type of convergence. So if it were converging, and once it got close, it stayed close over the whole range, we call that uniform convergence. So it gets close and it stays there. This is a form of pointwise convergence. So it's converging pointwise, but it is not converging uniformly. And so sometimes in higher level stats classes, they'll take you through all this convergence type stuff. A lot of the examples that you see in those classes are fairly trivial, but I would say this is a real world example of why you might want to be uniformly convergent. So I'll say more about that as we go through the class and tell you what different types of convergence are. Okay. Any other questions about the homework? And if you did say 2,500 or something like that, I'm okay with that. I don't think UE would mark off more than a point for that. So just as a reminder, but if you guys understand the message, that's all that really matters. So if UE does take off a point on things, it really is just a heads up. You might want to look at this a little bit more, but we're not going to mess up your grade. So losing a point on a homework will never change your overall grade. So if it comes down to that 1 point, I'll always round that. Okay, we are right in the middle of this conversation with the normal example. So our example was xi coming from a normal distribution with unknown mu, and we said this was known. We'll do the problem again, and we'll treat that as the unknown. And later on the homework, you can treat them both as unknowns. And ultimately, you'll be solving all the integrals that we've solved in class. You'll just be doing it in a slightly different order. So I'll have that homework posted later this afternoon. Okay. Everything's IID. So we've got n data points. And we want to find this thing. Posterior predictive distribution. And I like to write down that sigma just so that I can remember that I know it. So it wouldn't, if I were writing a paper or something, I might suppress that notation. I'd probably always infer it though. So I don't think I've ever had a case where I'm like, I've got no sigma. It's never happened in my life. Okay, so it was just this integral right here where we've got f of x tilde given mu and sigma squared, and then we got our posterior distribution. Sigma squared. I could write, if you like following probability rules, I could write x in there. It's conditionally independent given that you know mu. So those functions would be identical to each other. So you're just going to integrate between negative infinity and infinity. This right here was a normal with mean mu, variance sigma squared. And this right here is a normal, mean x bar, and variance sigma squared over n. We've assumed the flat prior. And we could give several good reasons for choosing that prior at this point. Integrate over mu. And we worked through this integral in excruciating fashion last time. And if you recognized in the first step of doing that integral, if you recognize this thing's going to be a normal, the only question left is which normal is it? So what is the expectation and the variance? If I know those two things, I've defined the normal. And so we worked through this thing. Does anybody remember what the answer was? It was normal. It was centered at x bar, big surprise. That's it. So we solved that, and we did a lot of work to do it. I kind of still like integrating. So when I'm at my desk, or at home or something like that, I like doing a good integral problem. I hate doing it for tests. I'll probably ask you to do this integral on a test, so you should just be really well practiced at it. Saying that, I'm never going to throw just a crazy integral at you and hope you can figure out all the tricks to remember that sort of stuff. So you can do that in luxury at home. Okay, we kind of understood that this was the variance associated with our sampling point. We could never get away from that, no matter how big n is. And this is our variance that's attributed to estimating mu. And so maybe we could have just intuitively surmised that that was going to be the variance. My intuition only works when I already know the answer. So usually wrong. So here's another way to do it. So the iterated forms. So these are for expectation and variance. We've already written those down. That was going to be the expectation of something in general. I'll say z is equal to the expectation of z given w, the expectation of that thing. So this is over z given w, and this is over w. And this expectation is over z. So that notation is telling us which random variable we're integrating against. There are different notations out there. So I think Peter Bickel in his book, he likes the notation, instead of telling you what you're integrating against, he tells you what everything else is fixed. So he does it exactly the opposite way that I do it. I hate that notation. Saying that, I can get used to it. So I think this is the more conventional thing. And also we have a formula for variance. So z is just a random variable, w some other random variable. This thing is the variance of the expectation of z given w plus the expectation of the variance z given w. We applied this formula last time, so we'll do the variance one in just a moment. But the way we use this is we just apply it to the posterior distribution. This is going to be conditional on x. I'm going to remind myself that I know sigma all the way through the problem. And this was just the expectation of x tilde given mu x and sigma squared. And I should probably make sure I build in some notation so I know what I'm conditioning this expectation on as well. So everything is going to be conditional on an x and sigma squared. So I have that information here. And I have that information here. So this expectation pertains to, this conditioning pertains to that expectation, and this conditioning pertains to that expectation. And these are really exactly the same formulas. I've just conditioned on everything that I know. And so we worked this out. We knew what this expectation was. Again, I can get rid of that. We don't need that. And it's for the exact same reasons we were able to drop this out of the notation. That's that same integral. This is that same layer. Is that right there. So we get rid of that. This is just an the x tilde. We know how it's distributed. It's normal with mean mu and variance sigma squared. That's this. So there's an analog between this iterated form and that integral. So this is going to look like the expectation of mu given x in sigma squared. Here, the conditioning on x is necessary. So it's informative about that parameter right here. And this is the posterior expectation. And we know what the posterior expectation is. It's x bar. That's this. That x bar right there. So all the things in the integral are also appearing in this iterated form. Keep in mind, these expectations are integrals. And we can do the same thing with variance. Let's do that. So the variance, we knew what that was, sigma squared plus sigma squared over n. I think I just erased off forward. But we can apply the exact same thing. I want that variance right there. So I'm going to use this formula and just plug everything in, where this is acting as my C right here, and mu is acting as my W in that formula. So this is going to look like the variance of the expectation of x tilde given mu, sigma squared, and x. And this has to be conditioned on x and sigma squared. So again, same rationale, I've conditioned on x and sigma squared. And I sometimes scramble my notation. It doesn't matter, I just am indicating that I know all that stuff. This is going to be plus the expectation of variance of x tilde given mu, sigma squared, and x. And this is going to be conditioned on x and sigma squared. So 2 layers. So this thing, same thing, we've done before. We already know what that expectation is. We've dealt with that before in the previous problem. So that appeared right here. The interior expectation. So one of those things that you already know from the expectation layer that appears in the variance layer right here. So this is going to be, I'll add the plus sign right here. This is going to be the variance of the expectation of x tilde, given that you know all this information. Same rationale. I don't really need x. It's not informative if I know all the model parameters. So this is going to be mu given x and sigma squared. And this is going to be the expectation of this variance right here. So the variance of x tilde given that I know everything in the problem, I even get the data, but the data is not informative given that I know the model parameters. So if I know what model generated everything and I know with certainty their model parameters, the data isn't useful. So it's just a proxy for inferring those things in the first place. So what's the variance of x tilde given mu and sigma squared? You know it. It's that right there. So that's going to be sigma squared given x and sigma squared. This is why I like the notation. So I can remember, I know sigma squared with certainty right here. So this is not a posterior quantity right here. So this one, however, does have something to do with the data, at least in terms of n. So this is the posterior distribution from mu, given that you know sigma squared, what's its variance? This is going to be sigma squared over n, the top one, that's that. So all the things in the integral you are using. And then sigma squared, given that the expectation of sigma squared, given that you know sigma squared, you don't need the data for that if you know sigma squared. If you try to estimate sigma squared and you know it, that's a mistake. So this is sigma squared. So sigma squared plus sigma squared over n. So it saved us a lot of work to work through everything. Basically, we're just regurgitating knowledge that we already know when we work through that integral. This was integrated with respect to mu. I think I erased that right there. This integral, what you're integrating with respect to, that would be the random variable you would condition on in the problem. It always works out that way. We'll do another problem in a couple minutes. So we'll see that again. Let's at least do a quick proof of the iterated expectation. And I'll leave the proof for variance to you if you want to check it out. It's in any standard inference book. So they're used all the time. Okay, so let's just write out. So say proof of expectation, and I'll go back to our original generic notation. Expectation of z is equal to the expectation of the expectation of z given what we I probably want to be polite and tell you what those expectations are over. So for me to solve problems right, I need the right notation. And then I kind of get a little bit robotic for a second after I set it up and I just kind of do the calculus. Okay, so what's this thing? That's in your first stats class, you learn what that is. So we're integrating with respect to z's distribution. So what's this thing? Right here, this is two integrals. So the interior integral, this part, right here, that's just going to be the expectation of z. So it's a function of z, but I'm going to be integrating with respect to the conditional distribution. F of z given w. I'm assuming everything's a continuous random variable. If it's something discrete, you'll just replace all my notation with sums. So, and this is going to be dz. So that's what that interior expectation represents. It's that conditional distribution. Expectation of z with respect to that distribution. And then I need to take the expectation of this whole quantity. So this is now just some function. So, and I want to take the expectation of it. What do? I take the expectation of that thing. It means I integrate it with respect to its distribution. And the random variable there is w. So I'm going to integrate this whole quantity with respect to w's distribution, its margin. So that's what that means. I think the first time I saw this, it was like, what does that even mean? Once you write down the integral, then you understand what it all means. So, and now we just need to prove that these two things are the same. So what I'm going to do is I'm going to slide that inside right there and get the joint distribution. So give myself some space. So that's going to be integral z f z given w times fw dz dw. So I haven't changed anything. This is the joint. So this is going to be f, z, and w. Now I'm going to do the one magical step in all of this. I'm going to interchain interchange the order of integration. So I'm going to swap those around. This is called Fubini's theorem. There's other names for it, but generally Fubini gets the credit for this one. And the question is when can you interchange integrations? When did they teach you you could do this?
Under the multivariate calculus?
Yeah, so do they teach you when you can do this?
There's a technical condition, but I think the most useful case is like continuous functions if you do the interchange.
Continuous functions, yeah, we're assuming everything's continuous. It better be continuous if we're integrating. So there's other conditions on it. Do you remember any of them? You just gotta try it and you see if the left and the right hand side are actually the same things. So that's kind of the best way I can think of doing it. Try it, see if they're the same. If they're not the same, then it doesn't hold. What are the basic conditions for it holding? Do you know?
Finite variance.
Finite variance sounds good, but yeah, exactly. It's a condition for another thing. I don't think that's it. So it turns out if the integrand is positive, you can do it. So if it's a finite variance function and it's positive, you can do that. So you could do that with things like probability distributions. We won't prove that. You can always do it when the space is bounded, i.e. it's compact. You can do that. When you have unbounded spaces, sometimes you have to be careful. And so there are conditions, and if you go to Stack Exchange or something like that, they might enumerate everything for you. But probably you need a measure theory class if you want to know all the conditions. So if this is a measurable function in the first place, you can do it. And so what we're assuming is that the left-hand side even existed. So this isn't necessarily positive right here, so we can't apply that. But if it's a measurable function, then you can do it as well. The densities don't mess anything up because they're always those positive functions that are measurable as well. So they represent measures. That's what we use them for, to measure things between 0 and 1. So for expectations, you can do this. There's only a couple times that I've worked through problems where it's like, oh, it doesn't hold. This makes a big difference. So a lot of times it holds. Okay, so it holds in this case. This thing is measurable. The expectation exists in the first place. So we might say if the expectation even existed, then we might be able to do it. And we're only going to apply the formula when the expectation exists. And so this thing is just going to be integral C, F, Z, and W to join. dW, dz, there's my Fubini step. So I've done the interchange. And because Z doesn't have anything to do with that, I can just pull Z out and move it. And this is an easy integral to do. We're going to average away W. We're marginalizing it out. And so the interior integral is now just Fz because W's gone. What do we do with W? That represents an averaging across W. So that's Z, Fz, dz, proof completed. So it really is just identity. If you want to prove an identity the typical fashion, if you know what the identity is work out the left and right hand side until you recognize them as being the same. So we won't do variance, it's just a little bit more algebra. I won't test you on it either. I'll just hope that you can remember it. So let me say it this way. If you remember it and you can apply it, that will help you in the future. It'll help you in this class. It's almost guaranteed to speed up a problem on the midterm. And if you don't know it, you don't know your expectations and your variances for different distributions, that problem will be extremely difficult because you'll probably have to work through like an infinite sequence or something like that. If I do an integral on a discrete random variable, you'll have this infinite sequence and you'll have to remember how to do that. And sometimes people do remember how to do all that stuff, but usually you have to fumble around with it for a couple minutes and you don't have time to figure it out on a test. And so you will want to know all your expectations and variances for distributions that we touch in this class, unless I say otherwise. So your list should be evolving. We'll see a new distribution, I think, by the end of this class. We'll definitely get into it in the next class. Any questions about this before we move on? Let's do one more problem. You will use this in the homework, but you'll be doing all these steps in a different order. So I'll be asking you to figure out what the posterior predictive distribution is when you don't know any of the model parameters. So the realistic case. Let's look at another like kind of fictitious case. So let's try to find pi x tilde given x and mu. So that we'll do every version of this and not do the joint version that I'll leave for your homework. So how do we do that? This is going to be integral pi x tilde given, or this will be f x tilde, the sampling distribution, given mu, and I'll switch my notation to phi because when I integrate, I like thinking about gamma distributions. So perfectly arbitrary reason that works for me. So we'll stick with this precision representation. And I'm going to integrate this thing with respect to its posterior distribution. Again, I'm saying we know mu. I will have you work through this without knowing mu and do that integral. You'll have to complete the square to do it. It will be a repeat of the steps I did in the last class. So you'll get to see every different variant of these distributions. We're going to integrate across phi. Phi goes from 0 to infinity. So we need to figure out what, that's a theta. We need to know what that distribution is. I think we've done it before. We also need a prior to come up with that distribution. So let's agree on a prior right now. Which prior? I like it. I'm not going to argue with that. Proportional to 1 over phi, so this is the conjugate limit. So it's not actually a gamma distribution, it's improper, and we've already seen good benefits for using these improper priors. So we need to figure out what that thing is. This looks like the likelihood of phi given x and mu times pi phi. So it's going to be proportional to that. So I'm going to recognize everything up to proportionality just like we've done on almost every example. I think the next class I'll hold on to the normalizing constant so you can recognize what the distribution is. It's the only problem I think we do like that. Okay, so the likelihood function is just phi to the n over 2, e to the minus 1/2 times phi sum of the xi's minus mu squared. Pi goes from 1 to n. So I just took a normal distribution and I producted it up. So hopefully we're at a point where we can recognize what the likelihood function looks like in a GIF, and then I'll multiply by my prior. And so I can recognize this distribution as some gamma. So this whole thing just looks like phi to the n over 2 minus 1 e to the minus, I'll say phi, sum of the xi's minus mu squared over 2. So I can start recognizing that as a gamma. And then I can write down this distribution. And so this is going to look like phi to the 1/2 e to the minus 1/2 x tilde minus mu squared, and I'll throw the phi right there. When I product those two things together, I have some gamma. So this thing is going to look like this. Integral phi to the n over 2 minus 1. Maybe I'll do it in the right order so that it matches. So I'll write down the sampling distribution first. Phi to the 1/2 e to the minus phi x tilde minus mu squared over 2. So that's the sampling distribution. You'll recognize I've thrown away the normalizing constant instantly. It doesn't help us to recognize anything. And so I usually just toss it. Times the posterior distribution, at least the thing that's proportional to the posterior distribution. So this is phi to the n over 2 minus 1, e to the minus phi, sum of the xi's minus mu squared over 2. d phi, we're integrating between 0 and infinity. So this is going to look like phi to the n over 2 plus 1 minus 1. So I've just combined those. I always leave the minus 1 dangling out in front because that's what gives us the ability to recognize which gamma this is. So we'll look like e to the minus phi, and then we're going to combine the exponent. X tilde minus mu squared over 2 plus sum of the xi's minus mu squared over 2 d phi. If we were in calculus class, we would panic and go, how do you solve this? And you'd start thinking about parts, and hopefully you remember the formula and how to do it. But we have life a little bit easier because we recognize which distribution that is, and we know it's normalizing constant. And so this looks like a gamma. And it's defined by 2 parameters, alpha tilde and beta tilde. Where do I recognize alpha tilde? It's right there. And beta tilde is here. And so I know what this thing integrates to. Somebody help me out. What is it? I'll do the easy part. It comes in a fraction. Gamma alpha tilde. Sweet. Everybody knows. So it's that thing. And it turns out that's just going to have the n's in there. So that's just going to be a number. And so this thing is proportional to beta tilde raised to the minus alpha tilde. So we can write out the whole thing. This is going to look like gamma to the alpha tilde, which is n plus 1 over 2. And then we're going to have this thing, x tilde minus mu over 2. That's squared plus sum of the xi's minus mu squared over 2. That's beta tilde. And so, oops, I don't know why I did that. This is going to look like x tilde minus mu squared over 2 plus sum of the xi's minus mu squared over 2 raised to the n plus 1 over 2. That's what we're doing there. So this is our posterior predictive distribution. Oops, given mu, proportional to that. So I can just get rid of any proportionality constants. The 2's nicely disappear there, and that thing is just a constant as well. So those are all just numbers. Doesn't change the shape of this thing. This is a random variable over x tilde. And so we just need to recognize which distribution that is. Somebody help me out. Which disk is it? At least the family. Somebody said it. T. So it's some T. And we need to get it in the right form. So we'll do the exact same thing we did last time. So this is going to be proportional to, and I basically need this thing to look like this. So a T disk, so T densities look like this. 1 plus, I'm going to let Z be my random variable. I'll use the same centering notation since it's the typical thing. What goes down here? Sigma squared, the scale of everything squared, and the degrees of freedom. What goes here? Mu plus 1 over 2. Later on, it's useful to just start ingraining this into your memory. That's going to change to the dimensionality of the problem. So you'll use that later on. So T densities look like this. There's a normalizing constant, the gamma, to the nu plus 1 over 2 divided by gamma nu over 2, square root of pi times mu. How do I know that? I just looked at it too many times in my life. So I've never used it for anything though. The real reason I know it is because I went, essentially when I was taking this class in college, and I was introduced to a T distribution, and I asked the professor, what does a T density look like? And he said he didn't know. Off the top of that, nobody knows. You know, you just look it up in the table. So I found that kind of unsatisfying. Certainly people know what they look like. So Bayesians always know their distributions and all their properties because everything is based on distribution. Okay, so we just need to make this thing look like that. I'll finish it up over here. So what am I going to do to get that 1 right here is I'm just going to, that's the random variable. I like where it's sitting. It looks real nice. I can already recognize the scale of that, or this location parameter. So I'm just going to divide by this and do another factorization. So I'm just going to factorize that term out. So this is going to be proportional to 1 over, and I guess I won't write it as a fraction. I'll write it as this, minus n plus 1 over 2. We can already see the degrees of freedom on this thing. So this is going to be proportional to 1 plus x tilde minus mu squared divided by sum of the xi's minus mu squared. That's it. Hope everybody can see what I did here is I've just divided by that quantity right here, top and bottom, and I factorized one of them out. And so when I divided by sum of the xi's minus mu, that one turned into a 1, and now it's over here. So there is another layer of proportionality. And if you want to see that slower, go back to the video where I did this the first time, and we wrote it out in excruciating detail. So this function is proportional to that. Now, of course, if mu was the random variable, we would have had to be way more careful, but it's a constant in all of this. So we're able to factorize those things out. And so I need to recognize the degree of freedom. I need that to be sitting right here, and it's not there. So I know how to get it in there. I just multiply by some funny version of 1. And now I can recognize it. So this is the degree of freedom. Has n degrees of freedom. The scale parameter is the square root of that thing right here, and the degrees of freedom is n. So this is a t. The location parameter is mu. No surprise. If you knew mu, you're still going to be centered there. This is going to be sum of the xi's minus mu squared over n. If you knew mu, this is an unbiased estimator of the variance. Since you know mu, you gain a degree of freedom in the problem. So it's not your typical n-1 degrees of freedom, because you know mu and you don't have to estimate it with x bar. So all I'm saying is that's an unbiased estimator of sigma squared. So that's a nice property. So Bayesian is going to come up with probably the exact same intervals that a non-Bayesian would come up with. So it's another one of these problems that the Bayesian and the non-Bayesian are aligned. When we get into hypothesis testing, what you do with this distribution, Bayesians and non-Bayesians are going to heavily disagree with each other. So there's something to look forward to if you like drama. So far, everybody gets along. We're just seeing different ways to think about things. One thing I want to point out is that a t-distribution is a normal scale mixture model, where I mix the scale parameter over a gamma distribution. So in general, t's, this, I'll write it down, are scale mixture models. Where my mixture weights are gamma distributed. So just in general, if we do something like this, if I have an integral, this is what a scale mixture model looks like. If I take an integral, let's say this is x, this is maybe normal distribution, so I'll call this thing normal. And I end up taking that and I redefine 1 over sigma squared as phi. So it's actually mixing over the precision in a gamma sense. In an inverse gamma sense, it's mixing over the variance. So 1 over sigma squared is equal to phi. And so if I take a gamma distribution on phi with some parameters, alpha and beta, d phi, this is a t-distribution. Specifically, this will give you a t-density if I integrate between 0 and infinity. So this is a scale parameter. This is a mixture weight. What am I doing? Is I'm averaging the normal distribution over a gamma distribution. But I'm averaging the scale parameter. And so this is what's called a scale mixture model when you do that. And T's are a scale mixture of normals with inverse gamma on the variance or a gamma on the precision parameter. That's always true. Question is which t-distribution is this? So what do you think the location would be? So we've got location, scale, and then our degrees of freedom. It kind of depends on what these parameters are. So let's say I wanted the degree of freedom to be mu in all of that. It turns out I can control that through alpha and beta. The location of all of this, I haven't changed any of it. That's going to be the same. The scale is going to be the same parameter over here. We're integrating over this, so it's going to have something to do with x. We'll look at it later. It's going to be the x minus mu squared thing. I'm going to have you guys work it out. But you can control the degrees of freedom through these parameters right here. Later on, I'm going to have you work out what alpha and beta need to be for nu to be, for this to have degrees of freedom nu. I'll tell you what it is. Later in, I think the third homework that you'll do, you'll get this exercise. If this is nu over 2 and nu over 2, then this is going to create a t distribution with degrees of freedom mu. Later on, you'll see that. You'll work through it. So I'm giving you a heads up. It's a typical midterm test question that I usually ask. So Very often, I like to work when the degree of freedom is 1. So that actually makes really heavy tails. That's called a Cauchy distribution, and they can be very, very useful. And unfortunate for t-distributions, if you write out the likelihood function for it, it's just a big product that you can't simplify. So, but you can simplify this in terms of sufficient statistic, the normal, usually using x bar or something like that. And this is an easy distribution to work with. So these mixture representations will become useful once we start doing things computationally. And you don't want these huge products in your code. It'll mess everything up. So we'll come back to this representation a little bit later. Next time, I think what we're going to do is we're going to look at the Poisson distribution and kind of repeat these exercises. So let me just write down a Poisson for you, and then I'll let you go. Poisson. Dist. So this is the mass function for it. It's a probability of something, and it's controlled by one parameter. Somebody help me out. What does a Poisson look like? E to the minus lambda, good job. Lambda to the x, x factor. That's it. So lambda has to be positive, and x represents counts. So x is an element of the counting numbers, 0, 1, 2, 3, 4, so on and so forth. So it goes off to infinity. So they're distributions that can help you to count things. Does anybody know what the expectation of the Poisson is? It's lambda. What's the variance? Same answer. That's an interesting thing. We're going to talk about that just a little bit. But the variance and the expectation are the same. If you saw a real data set and you saw the expectation and the variance were the same, would you believe it? I probably wouldn't believe it. They might only be close. Of course, with real data, they don't only be close. If you saw a counting model and the variance was much, much higher than the expectation, would you think it's Poisson? You would. That's called over-dispersion. If you saw data and if the variance was much, much larger than the expectation, would that worry you? Freak me out. We're going to talk about that as well. So, talk about that really can't happen. What's the conjugate prior for lambda? Gamma. We'll look at that. What's the posterior predictive distribution? Harold's got it. It's a negative binomial distribution. So let's come back next time, look at a negative binomial, and chisel through those calculations, and talk a little bit more about mixture models, because a negative binomial is a mixture of a Poisson with a gamma, just like a t is a mixture of a normal. We'll come back and talk about all those things, familiarize ourselves with these distributions, and pretty soon we'll be moving off to Monte Carlo. So I want to get into that within the next week or so. Just remember, next Friday we won't be having class. We do have it this Friday. And if you guys haven't checked your calendar, the Friday after that you also have off for fall break. So we'll meet on this Friday, and then we'll get 2 Fridays off. Cool. Thanks, you guys.